Bismillahirrahmanirrahim. Good evening again. Let's keep going to complete this lecture. Like I said at previous video, we was talking about and try to do appropriate summary to current induced electric resistance in this component. Now I have this inset plot between current and T service. Like I said before, from this white ball started from 30 Kelvin, the service temperature, and after that, when increasing the current from 0 to 20 milliampere, it's increased to be approximately 100 Kelvin, and with red balls, approximately more than 100 Kelvin. Now, when the bias temperature is 50 Kelvin, I'm talking about the red balls, it's approximately more than 100 Kelvin. And at the highest currents, like I said before, 20 milliampere, at higher bias temperature, that's mean here, more than or approximately 150 and more than, the IV characteristics become almost linear. Now I'm talking on this curve, IV, at higher temperature, more than approximately 150 or more than, the IV curve is approximately linear behavior. Let me I lost my slide. Yes, at high bias temperature, like I explained before, the IV characteristics become almost linear, and a negligible change is observed in a corresponding T service of the sample. Negligible change. We can say it's all of these are liners, are lines without change, or approximately we have some change, but we can negligible it. We can ignore it. All that from 150 Kelvin and more than at high temperature bias. Here we have a question. Why the T service doesn't change with high temperature and change with low temperature, less than 150? Here, this explained to us. This plot explained to us we have two different states. The first one, 150 and more than, it's isolating state, antiferromagnetic, and less than 150. This period, the hysteresis phenomena, non-linearity behaviors. Here, less than 150. This is isolate. This is metallic state. That means ferromagnetic. And here this plot explain to us these two periods. From here, it's isolating, less than, more than isolating metallic transition, and less than TIM, it's metallic. Let's take a look what that means. What that attracts about the isolating state or metallic state. What will happen? What the relation between the T service, the temperature, and the isolating state or metallic state? Here, actually, at isolating state, the temperature doesn't change because it's approximately equal the service temperature, but the different change, the different behavior will act at the metallic state at less than 150 Kelvin. Some relation when we increase, some change, yes, non-linearity behavior start from bias temperature, and after that, when we increase the current, the curve will increase to reach the maximum point. Here, actually, Rebello he was a great researcher because he could plot the IV current and at the same time measure the T service of the samples. This plot is very clear. IV, plotted IV curve, and at the same time measured the service temperature to the samples. Here, the material in heat up are the isolating anti-ferromagnetic, like I said before, and the T service is constant. But at the metallic state, ferromagnetics doesn't heat up and the T service is increasing at less than 150. Like I said before, isolating state, metallic state, and the current will flow will increase from 0 until 200 milliampere. Here a small conclusion, a simple idea, simple conclusion about the high temperature charge ordering isolating phase is kinetically arrested and during cooling. It's another interpretation, another explaining to support the first idea about the oscillating, the temperature doesn't change. At the metallic, the temperature changes. Here, at the high temperature, 150 or more than, charge ordered isolating phase is kinetically arrested. Arrested where? Arrested at the during cooling. That's mean at less than 150. This behavior, this arrested process will be, and it can coexist with the ferromagnetic. Ferromagnetic where the ferromagnetic at the metallic state, like I said, less than, that's mean at less than 150. Now we can say the state of material is important because that we can know from the kind, from the state's kind, the temperature will change or not. And we can say it's early to conclude the electric resistance, closer electric resistance effect is cased by the Joule heating alone. Now here we have a good question, but unfortunately I couldn't find the answer from this article. Maybe you can take this answer from another article, I don't know, but Rebello didn't explain any information about why the T service is increasing in metallic state. Why the temperature is increasing in the metallic state. For here, for example, from 0 to 20 milliampere to reach here 100 Kelvin or maybe more. Now I have simple questions. I have simple equations about the resistance, resistivity, what equal the resistivity, resistivity equal resistance times square current. But here I have interesting thing. But at first we must do some equation math to prove that. Let's start from the resistivity equal resistance time square of current, and after that let's calculate the heating. Heating equal resistivity dot delta T. Here small t, that's mean time, not temperature. That's mean resistivity dot delta T. We know the resistivity equal resistance times square of current. What that's mean? That's mean heating will equal resistance times multiple current dot delta T. Let's put this equation between two brackets. Now let's take, for example, a two different resistivity point at these two different states, isolating and metallic. Let's start from isolating more at the period who's more than isolating metallic temperature. Let's be this one. This is the resistivity equal, for example, resistivity X resistivity. But Let's take another one. The metallic state, let be at the same line, and will equal that mean the same X resistivity. Now I have two equal amounts of resistivity at different states, metallic and isolating. Now let's calculate the power and let's prove another interesting thing. The power at the isolating equal what? Equal resistivity at isolating dot multiple current. The same thing with power at metallic equal resistance at metallic at ferromagnetic dot multiple current. When resistivity 1 equal to, what that's mean? That's mean power at isolating equal power at metallic. Let's be like that. Let's be like that, sorry, the power. Now, what about the heating? The heating at the isolating equal the heating at materials. At material, we have same amount of heating at two different states and the same amount, the same result of power with different states of metallic and isolating. It's interesting results, equal results with different situations, with two different situations. This the last plot and this the reference slide. Our lecture is done. This lecture number 2 was talked about current induced electric resistance in this component. Have a good day. Thank you about your watching or listening. See you in the next lecture.